Berkson's paradox. Let's see. Have you ever wondered why in your neighborhood restaurants, those that serve good burgers end up serving bad fries and those that serve good fries end up serving bad burgers? The truth might be that you probably do not go to those restaurants that serve bad burgers and bad fries because they probably have bad ratings, and you probably exclude that section of restaurants which serve really bad food. And if you look at the remaining restaurants, the fries or burgers, one of them is probably better than the others. And there are probably very few restaurants that actually serve very good burgers and fries. So if you look at the sample of restaurants that you go to, excluding the very bad ones, you will end up seeing one of them is better than the other. And you might end up thinking that restaurants that serve good burgers serve bad fries. And this might not be the right conclusion because you only looked at a subset of restaurants and you excluded some restaurants here. So this is an example of Berkson's paradox. Let's look at another example. Again, a very interesting one. Let's look at dating scene. So people usually want to date folks who are both handsome and nice, right? And suppose I plot the handsomeness and niceness of people on a sheet of paper like this on blackboard. Probably these are not correlated. This is what I might have. But if I actually look at what really happens when people are trying to date, usually you might have a threshold saying, I want to date someone if they are, don't want to date people who are like, neither handsome nor nice. And that's probably, a filter that you have right at the beginning. So maybe what's going on in your mind is that you have a threshold. If you were to put like an equation to it, handsomeness plus niceness greater than some threshold, then you're okay to date the person. In other words, you're okay to date people who are at least handsome or nice. And if they are both, that's okay, that's a bonus and that's really good. What's really happening is you have eliminated this subsection of people whose handsomeness plus niceness is less than some threshold, let's say. And what is remaining is people on the top of this line. And if you look at only this section of data, you will see that handsomeness and niceness have a negative correlation. In other words, if I were to fit a line, you would see that it would have a negative slope if you exclude the points at the bottom here. But that does not mean that in general, handsomeness and niceness are negatively correlated. But yes, in the subset of people you're dating, they might be negatively correlated. So it's wrong to draw a general conclusion from the subset. You might also think, okay, people who are very handsome and very nice are probably out of your league. So you might actually exclude the uppermost section as well. And then you have an even narrower band and the negative correlation will be even more strong here, even more apparent. Right? So this is another example of Berkson's paradox where you might end up making an incorrect conclusion that handsomeness is negatively correlated with niceness. This is not true in general, though it might be the case in a small subsection of people that you're looking at. What you ended up seeing here is really selection bias, where you selected a subset of the population and you made a general inference from it. Let's see mathematically why Berkson's paradox occurs. Suppose you have two independent events. Like in this case, let's say whether a restaurant serves good fries or whether a restaurant serves good burgers. So these could be two events. Or it could be like, whether a person is handsome, whether a person is nice. And let's say they are two independent events. And if you consider only outcomes where at least one of these occurs, then these events end up being negatively dependent, even though if you look at the entire data set, these events were independent. So let's put this mathematically. Suppose we have two events, A and B, and we start with, there is no correlation between A and B. So P of A given B is the same as P of A. So A happening is not affected by whether B happens or not. Now let's put this in a concrete example. Now suppose I write down this table here. I have two events A and B. I write down all possibilities: A occurring, A not occurring, B occurring, and B not occurring. And I put down some odds here: 25, 25, 25, 25, where this is 25 is A and B occurring, 25 here is B occurring but A not occurring, and this is B not occurring but A occurring, and this is both of them not occurring. All of them are 25. So now suppose I want to compute probability of A given B. I would look at, since B already occurred, I would look at only this column, this row B, and I would look at the odds of A having occurred in that row, which is 25 out of the entire row 50. So that's half. And if I look at probability of A, that is this entire marginal probability for A is this entire column. So if I look at this column, I have 25 plus 25, odds of 50 out of the universe of odds, which is 100 here. So that's again half. And I see that P of A given B is the same as P of A, which shows they are not correlated in this case. Now, suppose I assume that at least A or B occurred. In other words, A union B occurred, right? And then I shared those parts of this table which indicate A union B occurring, which is all the yellow shaded region. So my universe is only the yellow shaded region now. And now having seen that A union B occurred, what is the probability of A if B occurred? So if B occurred, it's again this row. Probability of A given B occurring is 25 out of 50, which is half. But if I look at probability of A in this universe of A union B having occurred, now again I would look at this column, which is like 25 plus 25, 50 out of the entire universe of odds, which is only 75 in this case. So I have 2 by 3. The odds of A occurring given A union B occurred is only 2 by 3, right? It's 2 by 3 this time instead of 1 by 2 earlier, right? So what we see once again is that earlier P of A given B was the same as P of A, but if A union B occurred, P of A given B when A union B occurred is less than P of A when A union B occurred, right? And this is what is leading to the negative correlation that we see while things were originally uncorrelated, because we selected only a subset A union B here. Another popular example of Berkson's paradox is in the space of clinical trials. So suppose you want to find if the incidence of locomotor disease is correlated with the incidence of respiratory disease. So suppose you got data from a particular hospital to do your analysis, and then you looked at the percentage of people with locomotor disease for all people in the hospital, and that's the orange here, it's around 10%. And then you looked at two specific subsections within that hospital, those who have respiratory disease and those who do not have respiratory disease, and saw how many of them have locomotive disease. So percentage of people with locomotive disease was very high for those people with respiratory disease in the hospital, right? It was like 25%. But if you look at percentage of people with locomotive disease for those without respiratory disease in the hospital, it was again like less than 10%. And what this makes us think is that probability of having locomotive disease is higher if you have respiratory disease. But the problem here was again that of selection bias. The reality is that people with both respiratory and locomotive disease are more likely to make it to a hospital than people with only one serious condition, either respiratory or locomotive disease. So, because the more serious conditions you have, the more likely you make it to the hospital, right? So if you look at patients within the hospital, the inference that we drew is that locomotor disease is probably correlated with the incidence of respiratory disease. But if you do not look at the subsample of people in the hospital and instead look at the entire community, this is what we see. Orange is the percentage of people with locomotor disease. And now again, in the entire community, if you take the two subsections, those with respiratory disease and without respiratory disease, you see that the percentage of people with locomotor disease is roughly the same in these two communities. So what this again shows is that by selecting a subset of people in the hospital, we made an incorrect conclusion. Okay, So what can we do? Why do we care about all these examples? Why do we care about Bergson's paradox? What we are saying is that we should ensure there is no selection bias during data collection when we are trying to build our models. And when we do see a counterintuitive result, re-examine the sampling strategy. Think if there could be some kind of a paradox that is leading to this kind of an outcome. So to recapitulate, we looked at Bergson's paradox and saw how selection bias can lead us to make wrong inferences and see negative correlation in some subsections of population, while the entire population does not show any such correlation. Thank you.